Welcome to Digital Electronics Lecture 2, Part 1. Outcome of this lecture as follows. We'll learn the Fourier theorem, De Morgan's theorem, implications of De Morgan's theorem, universality of NAND gate and NOR gate, alternate logic gate representation, logic symbol representation, interpreting logic circuits. Fourier theorem. Fourier theorem helped to simplify logic expression and logic circuits. For single-value theorem, x is a logic variable that can be either 0 or 1. Each theorem is associated by a logic circuit. This is called single-variable theorem. So x dot 0 is 0, x dot 1 is x, x dot x equals x, x dot x prime equals 0. Similarly, so this is the dot product, this is the OR product. X plus 0 equals x, x plus 1 equals 1, x plus x equals x, x plus x prime equals 1. So all of this single variable theorem will be very helpful for simplifying purpose. For an example, the variable x may actually represent an expression containing more than one variable. For example, if we have a b prime, then a b prime whole prime, we can invoke theorem 4 by letting x equals a b prime. So if we take x equals a b prime, so this expression becomes, this is a b prime is x, then a b prime x, x and var x var, x into x var. So from theorem 4 we know x dot x bar equals 0. So this equation becomes 0. A b prime plus a b prime whole prime equals 0. The same idea can be applied to the use of any of these theorems. Multivariable theorem. In multivariable theorem, we have commutative law. We can write x plus y equals y plus x, also x dot y equals y dot x. This law indicates that the order in which OR and AND2 variable is unimportant. The result is the same. Associative law. X plus y plus z within first bracket equals x plus y plus z equals x plus y plus z. 12 x into y dot z xy dot z equals xy z. We can group the variable in an AND or OR expression any way you want. Distributive law. So we can write x into y plus z equals xy plus xz, or w plus x into y plus z equals wx, wy, xy, wz, xz. An expression can be expanded by multiplying term by term just the same as ordinary algebra. This theorem also indicates that we can factor an expression. That is, if we have a sum of two or more terms, each of which contains a common variable, the common variable can be factored out just as in ordinary algebra. Distributive law. If the expression is like that a b prime plus c plus a prime b prime c prime, we can factor out b prime variable as like this a b prime c plus a b prime c prime. If we take the common of b prime, it becomes a c prime plus a prime c prime. Consider the expression a b c plus a b d. Here two terms have variable a and b as common, so a and b can be factored out both terms. So that is, if we take ab common, ab into C plus D. Multivariable theorem. So multivariable theorem, x plus xy equals x plus x prime y equals x plus y, x prime plus xy equals x prime plus y. They are known as multivariable theorem. Multivariable theorem, this is the proof how x plus xy equals x. So we consider for case like x equals 0, y equals 0, or x equals 0, y equals 1, or x1, y0, or x1, y1. If you put x equals 0, y equals 0 in this equation, so left hand side become x plus x, that means 0 plus 0 into y is 0, and your right side is x equals 0, y is 0. So left hand side equals right hand side. Similarly, for x equals 0, y equals 0, your left hand side and right hand side is equal, which is 0. For x equals 1, y equals 0, for this expression, it also becomes left hand side 1, right hand side 1. For x equals 1, y equals 1, it becomes x equals 1, it becomes left hand side 1 and right hand side 1. So you can see for 4 of the cases, left and right hand side is same. That means x plus xy can be written as only x plus x square equals x, which is correct, or this is proved. This is another explanation. So you have x, y, xy into x plus y. So this x becomes x plus y. So note that the value of the entire expression is always same as x. So whatever value of x, the x plus xy, the value is the same. Alternatively, theorem 14 can also be proved by factoring x and using theorem 6. So x plus xy, if you take the common of x, x plus y1, 1y, so that is x into 1, which is known as x, using theorem discussed before. Multivariable theorem. All of this Boolean theorem can be useful in simplifying logic expression, that is, reducing the number of terms in the expression. When this is done, the reduced expression will produce a circuit that is less complex than the one that the original expression would have produced. For example, we have y equals a b prime plus d, a b prime d prime. Factor out the common variable a b prime. Then using theorem 13. So if we take a b prime common, it becomes a b prime into d plus d prime. So d plus d prime equals 1 from theorem 13. Using theorem 8, then the term parenthesis is equivalent to 1. So d prime equals 1 from theorem 8. Then y equals a b prime into 1. And x into 1 means x from theorem 2. So it becomes y equals a into b prime. You just need to use different kind of theorem. You need to remember a couple of things to make it faster, though most of the theorem will be given in the exam, but for faster calculation it's better to remember the couple of things. Here is another example. Z equals a prime plus b into a plus b. So first you multiply a prime with a prime with b, then b with a, b with b. Then using theorem 4 can be written as a prime dot a equals 0 and b dot b equals b from theorem 3. So this becomes z equals then a prime b plus ab plus b. Then using the theorem 13, if we take the common of b, it becomes a prime plus a plus 1. So using the theorem 2 and 6, it becomes V, because that become to check with the theorem if you are still confused. And one thing you need to remember, whenever you are using any of the theorem, you need to write it as a side note that this theorem is used in this line, something like that. Otherwise, it will be not complete actually. Your answer will be wrong. There you have given another example. I suggest you try it by yourself using any of the theorem and simplify it. If you have any doubt, you can ask any question in the class. We can also discuss. Now the important is De Morgan's theorem. Two most important theorems of Boolean algebra were contributed by a great mathematician named De Morgan. De Morgan's theorems are useful in simplifying expressions in which product or sum of variables are inverted. Say x plus y prime equals x prime into y prime. X dot y prime equals x prime plus y prime. The sum of product like x plus y prime, this is your OR product, and it becomes AND product. Just invert of this one. So it has x plus y whole prime, it becomes just x prime into y prime. Again here x dot y whole prime, it becomes x prime y prime. This dot becomes this OR. Theorem 16 says that when the OR sum of two variables are inverted, this is same as inverting each variable individually and then adding this inverted variable. Theorem 17 says when the AND product of two variables are inverted, this is same as inverting each variable individually then ORing them. So this is example how De Morgan's was used for simplifying this expression. So you have a b prime plus c. So which can be, this is plus, that can be written as dot. So a b prime whole prime dot c prime. So here a b prime equals x and c equals y. The result can be found using the theorem 17. So a b prime whole prime into c prime, which becomes a prime plus b double prime into c, or simplified version a prime plus b into c prime, which can be simplified as a c prime plus b c prime. Given this example, we just need to use De Morgan's theorem. So remember one thing, your dot product become your OR product, or your OR product become your dot product. So just here A and C, you have OR product, so it becomes dot, and this dot becomes OR, and this BD, between BD, this is OR become dot, and A prime becomes A, if C becomes C prime, if B becomes B prime, if D prime becomes D. Just check here, so use the De Morgan's equation. So you have dot product, so it can be written as splitting of these two OR product, like A prime plus C whole prime plus D plus D whole prime whole prime. Then for this overhead, you can write it, so this plus, it becomes dot again. A double bar into C prime plus B bar into D double prime. So it becomes A C prime plus B prime D. We can think this of a breaking the large inverter sign down the middle and changing the AND sign to an OR sign, or vice versa.